When people talk about operating systems and security, there's a phrase that gets repeated almost like a law of nature. Linux is secure. Not Linux can be secure if configured properly. Not Linux has strong security features, but simply and absolutely, Linux is secure. It's said in forums, in classrooms, in corporate meetings, and in countless YouTube comments. Over time, it has hardened into something more than an opinion. It has become a myth. And like many myths, it contains a grain of truth wrapped in layers of exaggeration, misunderstanding, and misplaced confidence. Today, we're going to unpack that myth and explore what Linux security really means, where the belief comes from, and why blind faith in any operating system can be dangerous. To understand the myth, we first need to understand its origin. Linux was born in a culture of openness, collaboration, and transparency. The source code is available for anyone to inspect, modify, and improve. In theory, this means vulnerabilities can be discovered and patched quickly because thousands of developers around the world are able to review the code. Compare that to proprietary systems, where the inner workings are hidden from public scrutiny. The open source model created a perception that Linux was inherently safer because many eyes were watching. The idea sounds reasonable. If everyone can see the code, surely someone will spot the problems. But the many eyes theory is not a guarantee. Just because code is open does not mean it is thoroughly audited. Large code bases can contain millions of lines, and reviewing them requires expertise, time, and incentive. In practice, much open source code is maintained by small teams or even single individuals who may not have the resources for constant security audit. The assumption that openness equals security is comforting, but it's not automatically true. Security is a process, not a property bestowed by a license. Another reason for the myth is historical context. In the early days of widespread malware, the majority of viruses targeted desktop operating systems with massive user bases. Linux, especially on the desktop, had a comparatively small market share. Attackers are rational actors. They tend to focus on targets that maximize impact and profit. If most users are on one platform, that platform becomes the primary hunting ground. Linux systems, being fewer in number on consumer desktops, were less attractive targets. As a result, average users encountered fewer Linux viruses, reinforcing the idea that Linux was immune. But lower targeting is not the same as higher security. It is like saying a small village has less crime than a major city because it is inherently more secure. The reality might simply be that there are fewer opportunities for criminals as Linux gained dominance in servers, cloud infrastructure, and embedded systems. Attackers shifted their focus accordingly. Today, Linux powers a massive portion of the internet's servers. It runs in data centers, hosts websites, manages databases, and orchestrates cloud platforms. And unsurprisingly, attackers have adapted. Server-side exploits, privilege escalation vulnerabilities, misconfigured services, and supply chain attacks targeting Linux environments are common and well documented. The myth of Linux security also thrives on a misunderstanding of permissions and user models. Linux employs a robust permission system based on users, groups, and file modes. The principle of least privilege is built into its design. Regular users do not have administrative rights by default. System-level changes require elevated privileges. This structure is indeed a strong foundation for security. However, foundations are only as strong as their implementation. Users frequently circumvent these protections for convenience. They run commands with elevated privileges without understanding them. They install scripts from random repositories and execute them as root. They disable security mechanisms to make something work. The architecture may be solid, but human behavior often undermines it. Another component often cited is the modular design of Linux. Because it is composed of many smaller components, administrators can customize and harden systems to meet specific needs. Minimal installations can reduce the attack surface by including only necessary packages. This flexibility is powerful, but it is also a double-edged sword. Customization increases complexity. The more configurable a system is, the easier it is to misconfigure, and misconfiguration is one of the most common sources of security breaches. A perfectly secure kernel does not matter if a service is exposed to the internet without proper authentication. There is also the misconception that Linux does not get malware. In reality, malware for Linux exists and has existed for decades. There are rootkits, worms, ransomware variants, and botnets targeting Linux systems. Many Internet of Things devices run stripped-down Linux distributions, and these devices are often poorly secured. Botnets composed of compromised Linux-based devices have launched massive distributed denial of service attacks. The myth persists largely because average desktop users may not encounter these threats directly, but in the broader ecosystem, Linux is far from untouched. The conversation becomes even more interesting when we examine the concept of security through obscurity. Some Linux advocates argue that because fewer people use Linux on the desktop, it is less targeted and therefore safer. But obscurity is not a strategy. It is a side effect. If Linux were to dominate the consumer desktop market overnight, the threat landscape would shift rapidly. Attackers follow opportunity. They exploit the most profitable and scalable targets. The belief that Linux's relative safety is intrinsic rather than contextual ignores this dynamic reality. It's also important to distinguish between the Linux kernel and the broader ecosystem, commonly referred to as Linux. On peut appeler Linux is secure. What exactly are they referring to? The kernel, the distribution, the desktop environment, the package manager, the third-party repositories, the applications installed on top. A modern Linux system is a complex stack of components developed by different teams with different security practices. A vulnerability in any one of those layers can compromise the entire system. Security is not monolithic. It is cumulative. Package management is often praised as a security advantage. Centralized repositories mean users can install software from trusted sources. Rather than downloading random executables from the internet, this model reduces certain risks associated with unverified software. However, it also creates a dependency chain. If a package in a repository is compromised, or if a maintainer account is hijacked, malicious code can propagate quickly. Supply chain attacks are not hypothetical. They have occurred in various ecosystems, including open source communities. Trust is essential, but it is never absolute. Then there is the issue of updates. Linux distributions generally provide timely security patches. The open source community can respond quickly to disclosed vulnerabilities, yet updates only protect systems that actually apply them. In enterprise environments, patch management can be complex and delayed due to compatibility testing. In personal setups, users may postpone updates for convenience. Unpatched vulnerabilities remain exploitable regardless of how quickly a fix was released upstream. Security depends not just on the availability of patches, but on their consistent deployment. Let's talk about the server world for a moment. Linux dominates this space, and for good reason. It is stable, flexible, and efficient. But servers are high-value targets. Web servers, database servers, container hosts, and cloud infrastructure are constantly probed by automated scanners searching for weaknesses. Brute force login attempts, exploitation of outdated services, and privilege escalation attacks are daily occurrences. Administrators must configure firewalls, intrusion detection systems, secure shell settings, and access controls properly. A default installation might be reasonably secure, but production environments require continuous monitoring and hardening. The myth that Linux is secure by default can breed complacency. Containers and cloud-native technologies add another layer of complexity. Many containers run minimal Linux images. Developers often assume that because containers are isolated, they are secure. But container escapes, misconfigured orchestration systems, and exposed APIs have led to numerous breaches. The underlying host, often Linux-based, becomes a critical security boundary. If it is misconfigured or unpatched, the entire container ecosystem is at risk. Again, the security of Linux is not automatic. It is conditional. We should also examine the role of user psychology. Linux users often see themselves as more technically savvy than average computer users. There is a culture of learning, tinkering, and understanding how systems work. This is a strength, but it can also lead to overconfidence. Believing that you are less likely to be fooled by phishing, social engineering, or malicious downloads can make you less cautious. Security is not just about code, it is about behavior. A system is only as secure as its least vigilant user. Another aspect often overlooked is physical security. A Linux laptop with full disk encryption can be highly secure if properly configured. But if encryption is not enabled, or if weak passwords are used, physical access can lead to compromise. The operating system alone cannot compensate for poor operational practices. Security is holistic. It spans hardware, software, network configuration, and human factors. The myth also thrives because security is relative. compared to certain default configurations of other operating systems in the past. Linux may have offered stronger separation between user and administrative, but those other systems have evolved. Modern operating systems across the board implement sandboxing, permission models, encryption, and secure boot mechanisms. The security landscape is competitive and constantly improving. Clinging to outdated comparisons distorts reality. It's worth noting that many security tools are built on Linux. Penetration testing, distributions, forensic analysis tools, and network monitoring systems often run on Linux. This contributes to the perception that Linux is not only secure but the tool of choice for security professionals. However, using Linux as a platform for security research does not make it immune to vulnerabilities. In fact, the same openness that allows defenders to build powerful tools also allows attackers to study and exploit the system. Kernel vulnerabilities provide a concrete example. The Linux kernel is a massive and complex piece of software. Over the years, numerous critical vulnerabilities have been discovered, including privilege escalation flaws and memory corruption issues. When such vulnerabilities are disclosed, patches are released, but between discovery and patching, there is a window of exposure. Attackers who discover vulnerabilities independently may exploit them before public disclosure. No kernel, regardless of reputation, is free from bugs. The concept of secure by design is often associated with Linux, but design alone is insufficient. Security must be maintained through auditing, testing, and responsible disclosure. Open source projects rely heavily on community contributions. While many contributors are highly skilled, not all code is equally scrutinized. Some components receive intense review, while others may linger with minimal oversight. The uneven distribution of attention can create blind spots. Let's consider the enterprise perspective. Organizations that deploy Linux at scale invest heavily in security teams, compliance frameworks, and monitoring infrastructure. They use mandatory access control systems, enforce strict authentication policies, and conduct regular vulnerability assessments. In these environments, Linux can be part of a highly secure architecture, but the security arises from disciplined processes and layered defenses, not from the operating system alone. Remove those processes, and the security posture changes dramatically. On the desktop side, the myth can be particularly misleading. A user might assume that because they are running Linux, they do not need antivirus software, do not need to worry about malicious email attachments, and do not need to practice safe browsing habits. While the risk profile may differ from other platforms, it is not zero. Cross-platform threats exist. Browser-based exploits do not care which kernel you are running. If your browser has a vulnerability, your system can be compromised regardless of the underlying OS. There is also the matter of third-party drivers and proprietary blobs. Not all components in a typical Linux system are open source. Firmware, graphics drivers, and other binary components may be closed and less transparent. Vulnerabilities in these components can undermine the security assumptions of the broader system. Openness is not uniform across the entire stack. Another contributing factor to the myth is community culture. Online discussions sometimes frame Linux as the enlightened choice and other systems as inherently flawed. This tribalism can discourage nuanced conversations about security. Admitting that Linux has serious vulnerabilities can feel like betraying the community. But mature security thinking requires acknowledging weaknesses, not denying them. Security researchers often emphasize that there is no such thing as a perfectly secure system. Every piece of software has bugs. Every network has potential entry points. The goal is not absolute security, but risk management. When we say Linux is secure, we oversimplify a complex probabilistic reality. A more accurate statement would be that Linux provides powerful tools and features that can be used to build secure systems. Whether those systems are actually secure depends on configuration, maintenance, and context. The myth can have real consequences. If organizations underestimate the need for security audits because they trust the platform implicitly, they may delay critical investments. If individuals ignore best practices because they believe their operating system protects them by default, they increase their exposure. Complacency is one of the greatest threats to security, and myths breed complacency. At the same time, it is important not to swing to the opposite extreme and claim that Linux is insecure. That would be equally misleading. Linux has a strong security track record, a responsive development community, and a wealth of hardening options. Features like discretionary access control, namespace, groups, and advanced firewall capabilities provide a rich toolkit for defenders. The key is recognizing that these are tools, not magic shields. So what should replace the myth? A more mature narrative would acknowledge that security is layered and dynamic. It would recognize that threat models differ between home users, enterprises, and embedded devices. It would emphasize regular updates, careful configuration, strong authentication, and user education. It would treat Linux not as a guarantee, but as a component in a broader security strategy. Ultimately, the myth of Linux security persists because it is comforting. It simplifies decisions. It allows users to feel safe by association, but true security requires ongoing effort, critical thinking, and humility. No operating system, no matter how well designed or widely respected, is immune to flaws. The real measure of security is not the absence of vulnerabilities, but the ability to detect, patch, and mitigate them effectively. In the end, believing that Linux is secure without qualification is like believing that a lock makes a house invulnerable. A lock is important. A well-designed lock is even better. But doors can be forced, windows can be broken, and keys can be stolen. Security is a system, not a slogan. And as long as we remember that, we can appreciate Linux for what it truly is. A powerful, flexible platform that can be made highly secure, but only through knowledge, vigilance, and continuous improvement.